Welcome to 24th lecture on ECD, Electronic Circuit Design. And in this lecture, we will study MOS FET based push-pull amplifiers. Before this, we have been studying BJT based push-pull class AB amplifiers. But in this case, we'll study a push-pull amplifier based on metal oxide semiconductor field effect transistors, MOS FETs. Right. There are some advantages of using FETs as push-pull amplifiers. The first of them is that biasing them is of course simpler compared to BJTs, and they're not prone to thermal instability. We studied that due to temperature changes, the BJT-based class push-pull amplifier biased at this point near VCC, it becomes unstable and the current can increase without bounds. So this was the DCQ point, the DC load line that we studied in one of our previous lectures. So that makes the BJT based amplifiers prone to changes in temperature, and they become unstable as the temperature rises. So this was the DC load line, the vertical DC load line, looking strange looking vertical DC load line. And IC in the case of BJTs is directly proportional to heat, and it can cause thermal instability in BJTs. But in FETs, it's not the case. In FETs, the expression is reverse. The current ID is inversely proportional to heat, so therefore we cannot have this thermal instability that we encounter here. Right, in case of BJTs. So class FET based amplifiers are a bit better than BJTs in many ways, whereas ESD, electrostatic discharge, is of course a disadvantage of FETs. So that's a great disadvantage, because ESD, electrostatic discharge, can make an FET non-functional, but it's not the case in BJTs. So BJTs have their own advantages, FETs have their own, and they both have advantages and disadvantages to make amplifiers from. Right. So let's study the first class B amplifier circuit using FETs. In fact, MOS FETs. So these are two MOS FETs, N channel, MOS FET and P channel, and we know that they have VTN and VTP. VTN is the minimum voltage between gate and source that we have to apply to turn this transistor on. So this is gate, this is source, this is gate, this is source for this P channel, this is gate, source for this N channel. So in the positive half cycle, this N channel M1 transistor, it conducts, and during the negative half cycle, the other transistor conducts. So if we can, but of course there is a distortion problem, because this gates, to turn this transistor on, we need this gate to source voltage VGS to cross VTN, the threshold voltage for NMOS. So as long as this VGS is smaller than VTN, you don't have an output. So there is a distortion problem that we studied in case of BJTs. That problem is also here. To avoid that crossover distortion problem, we come to another circuit. We call it class AB amplifier, and there is a figure 9.19b in the textbook, and I've drawn that figure on the next page 2, which refers to a sample class AB amplifier based on MOS FETs, and that avoids crossover distortion too. Right. So for that circuit, a BJT is used to bias the class B push-pull amplifier so that it is always biased at VTN and VTP, the threshold voltages. So as long as this makes us able to get the output, as long as we apply the input circuit, or as long as the input voltage increases or decreases from 0. So this is exactly the same that we did for BJTs. In case of BJT amplifiers, if you remember, we used two diodes to bias the base voltage at 0.7 volt higher than the emitter voltage all the time, so that there is no crossover distortion for the applied AC signal. So this is the circuit that we talked about, this circuit given in figure 9.19b in the textbook, and I have drawn it too. This is actually an example we are going to solve, and this is a bit complex circuit involving a Q, this BJT, this is a PNP BJT, it's not NPN, it's a PNP BJT, and these two M1 and M2 MOS FETs. So if for this circuit we have one variable resistor R6, And this R6, why is it variable? Because we vary R6 so that we get this voltage equal to VTN all the times, equal to the DC voltage at this gate terminal, equal to VTN, the threshold voltage for N all the times, and this voltage equal to VTP all the times. So this is how we do it. So how would you bring this voltage at VTN and this voltage at VTP? And of course, if the magnitudes, most times their magnitudes are equal, so this voltage is at 0 volts DC. V out is at 0 volt DC. So given this circuit and the information that VTN and VTP, the threshold voltage for NMOS and PMOS, they are equal in magnitude, 2 volts. And we have to set the value of R6, this 5K variable resistor, so that the DC voltage at the output across RL is 0. So we want this output voltage to be 0 so that the AC voltage can swing on it. And then we, of course, we don't need any coupling capacitor on the output, because the output is based on 0 volts. It's swinging on 0 volts. We don't need any coupling capacitors, you know that. So IR1, starting from this current. IR1 would be the current. 24 is the upper end, the lower end is at -24, and these three resistors. So the current flowing in this circuit, assuming there is negligible current that flows out of this terminal, assuming this current is negligibly small. So the current in the main path is this 24 minus 24 divided by all these resistors R1, R2, and R3, and of course which is equal, and VB can be computed as the voltage drop across R3, or by writing KVL equation, starting from 24 volts minus the voltage drop here, minus the voltage drop here, minus the voltage drop here, minus this, and finally it becomes plus because it is minus itself. So VDD minus IR1, R1, R2 is the voltage drop. This is VB, or we can find out the voltage drop. We can find out this voltage VB, this voltage. If we call this voltage as VB, we can compute this voltage as 24 minus the voltage drop here, minus the voltage drop here. So VB is this one. So this is what we have done in this equation. VB comes out to be 21.5, and there is an important point. VE here is larger than VB. In case of NPN transistors, VB is 0.7 larger than VE, but in case of this PNP transistor, VE is 0.7 volts larger than VB. So VE is VB, because PNP BJT, VE is VB plus 0.7. So VE comes out to be 22.2 volts, and then of course we can compute IE. We know this VE, the voltage drop here is VE minus this 24 divided by R1 plus, 24 minus VE divided by R4 plus R5. So 24 is the higher voltage. So 24 minus VE divided by R4 plus R5 gives us 1.64 milliampere current. That is IE, and that is approximately equal to IC2. And VR6, of course, is VTN minus VTP. The voltage drop here is VTN, approximately VTN. The voltage drop here across 470 ohm resistor is negligible. So VTN is the voltage drop here, is the voltage available here. VTP is the voltage available here. So across R6 we have VTN minus VTP. Since VTP is minus itself, so VTN minus VTP is 2 minus minus 2, it becomes 4. That is what we have written here. So V across R6 is 4, and the current flowing through R6 is approximately the same as this IE, because IB is negligibly small. So the current flowing through this is approximately IE. Since it's IC, and IC can be approximately written equal to IE. So the current flowing through this would be IE. So R6 can be computed as VR6 over IE. So 4 over 1.6 for 2.4K. So we can turn the knob of this 5K variable resistor so that it gives a resistance equal to 2.4 kilo ohms. And this is the resistance. And this is the resistance that we should attach here, so that the upper voltage and the lower voltage are VTN and VTP, as desired, and the DC output voltage is 0, so that the output can swing on 0 volt reference as we want it to be. Right, that's all for this lecture, and in the next lecture we will be studying something more about class B amplifiers, and then finally we'll move to class C amplifiers. Thank you.